I received a question asking me to go through this set of equations and give some insight on what they mean. This first one is usually written like this, and it's the inverse of density. It's 1 over mass density. And mass density is the amount of mass something has, or how heavy something is per kilogram of uh, or sorry, how heavy it is in kilograms per volume of meters cubed of that material. Mass per volume. And the mass is in kilograms if we're working in the SI units, and the volume is in meters cubed. So if we take this little volume of anything, it would say, well, how heavy is this volume? So if this is of something light, then it's less mass density. If it's of something heavy, then it's more mass density, more kilograms per that meter cubed. And what this is called the specific volume. Which is kind of silly because it's just the inverse of mass density is specific volume. So really all we're doing is taking the inverse, we're putting volume over mass. So it's just literally, as it says, it's 1 over mass density. Therefore, since mass density is kilograms per meter cubed, then specific volume is going to be meters cubed per kilogram. Did we need to invent a new unit for 1 over mass density? Probably not, but that's what that one is. Now these are just unit conversions. Unit conversions, so a joule by definition in its base SI units is 1 kilogram times meter squared over second squared. A watt is a joule per second, so it would be a kilogram per meter squared per second squared each second. So this is a rate of energy. And another word for a rate of energy is power. Any type of energy is measured in joules. That's calorific energy, that is thermal energy, that is work energy, that is potential energy, that's kinetic energy, etc. All energy is measured in joules, and all power is the measure of joules over time usually in seconds. Then we have here a Pascal. This is pressure. Pressures are measured in pascals. Pascals are a force over a cross-sectional area. Or a Newton of force, for example, over a meter squared. And that we can break out a Newton into what a Newton is. A Newton is a kilogram meter per second squared. So if you then have meter squared in the denominator again, and you put kilogram meter per second squared here, cross out your meter squared, that's where you will get this. And then it is easy to see that since a joule is a kilogram meter squared per second squared, then that's the same as a joule per meter squared. Now, what do I think you always have to remember? It's always handy to remember that a joule is a kilogram meter squared per second squared. A Newton is a kilogram meter per second squared. You should always remember that power is energy over time. And we always have to remember that pressure equals force over area. So I would just keep in my head these 4 things, and then you would never need a formula sheet. A equals pi r squared is area of a circle, which we shouldn't laugh at because sometimes we forget the basic formulas. Now, if I look in here, I'm getting into ideal gas laws. And the ideal gas law is PV equals nRT. And this would be of gas 1. And PV equals nRT is also true for gas 2. But N is a number of moles of the gas that I'm looking at. And if it's like, all contained or moving at a constant velocity, uh, then um, then we're going to have the same, sorry, this is at like situation one and situation two of the same gas. So at position one and position two of the same gas. And then this is a constant of that gas. So if it is the same gas, then I can set them equal to one another. And I can set them both equal to NR. So let's go P1 V1 equals NR, because if it's the same gas, then NR equals NR. They're the same thing. So I can go P1 V1 over T1 equals NR, but that also equals P2 V2 over T2, just dividing by T. So therefore, the ideal gas law between, two spots in one sort of, thermodynamic situation or mechanical situation would be governed like this. And then, so that's where I get this equation from. And then it's a simple matter to be able to convert my V's to my Q's if my Q is flow rate in this case. And then I need to remember that Q equals AV, and that's volumetric flow rate, where this is area and this is velocity. And so what I'm talking about with these two equations is basically flow through a pipe, let's say, or, flow through, let's say, a nozzle that's going to get smaller over time. And then this is going to be A2, but cross-sectional area A1 is greater than A2. But this is position one and this is position two. So the flow rate Q, volumetric flow rate Q, which is volume meters cubed per a rate is over time, equals the area in meters squared times velocity, which is distance over time. Distance over time is meters per second. So that's what gives you that meters cubed per second. And we can say with confidence that Q1 equals A1 V1 and Q2 equals A2 V2, but volumetric flow rate stays the same. So if 3 meters cubed, let's say 3 meters cubed is going through from here to here, then 3 meters cubed has to go through from here to here too, because it's not compressible. So what that means is it travels a smaller distance here, it travels a bigger distance here over the same distance over the same amount of time. So therefore, this must travel a bigger distance across two than it did across one. A bigger distance over the same amount of time means velocity increases. So volumetric flow rate stays the same. Q stays same, which means, Q1 equals Q2. And in order to accommodate for that, if the area gets bigger, if A2 is greater than A1, therefore, of course, the velocity at the exit with the smaller cross-sectional area must be if A2 is less than A1, then V2 must be greater than V1. And those are our relationships. And what we can do is just take the relationship here of distance and cross-sectional area. Distance and cross-sectional area here. So area is in meters cubed, but then here, we're going to go area times distance over time. So what we have is area times distance is volume over time. And that's where we can we can solve for volume. And we can get volume in here. We can get Q in here for volume for a certain amount of time. So Q equals volume over time. Solve for volume. Q times time equals volume. Hang on a second. Therefore, V equals Q for a certain amount of time. So therefore, instantaneously, we can substitute in Q for V, which is volume, in this equation. So that's where I got this from. It is basically an ideal gas law, factoring in our Q equals AV. Okay, let's change colors to move on then to a next equation. This is Q equals MC delta T. This is heat flow. So I could put a dot over this to show that it's flow. But that is essentially just heat flow. And this is how much heat is flowing over time is equal to how much mass of that object is flowing over time times specific heat. It's basically how much energy is in that substance per kilogram per degree. Specific heat is a measure of energy over kilogram. Degrees Celsius or degrees Kelvin, they're the same thing, over a certain change in time. Oh, sorry, change in temperature. So we usually use an equation like this where there's a gradient, and let's say outside the temperature is it's cold outside, but it's warm inside. And what is the gradient of heat that goes across this wall section, insulated wall section, for example? Well, it depends on the specific heat of this wall section. Depends on how cold it is outside, how cold it is inside. And then it's going to, move and flow with respect to time, which is small q, and it's a mass flow rate. Then we can also measure Q as heat energy. Heat energy. Of course, energy is always measured in joules, no matter what the energy is, as a function of change in internal energy. And this would be used for a thermo problem where there is definitely, a system and it has some surroundings, has a system and it has surroundings. And you want to know how much Q, how much heat is going in to that system, or how much heat is coming out of that system. Basically, it's part of a first law energy balance. It is an energy that is going in. Changing my color again. Let's talk about this one. Oh, this is Q equals AV, which we talked about above, where let's say now I have a pipe with a large diameter, and it's going to go down to a small diameter here, A1, A2. Well, I say let Q1 equals Q2 because the amount of volume of this liquid flowing through has to be the same as the amount of volume of this liquid exiting because it's not compressible. So therefore, A1V1 equals A2V2. And this is what accounts for velocity increasing when area decreases. This is called the continuity equation. Okay, so the next equation here, the next equation is just a unit conversion again. This is BTUs is 3.14 times watt. So IV is current times voltage, and it's watts. It is joules per second. All right, so that's just a conversion to British thermal units from the SI units of watts. This next equation here is internal energy. This is enthalpy. Enthalpy. Sorry, up here I called it internal energy, but it's actually enthalpy. Okay, so this just says the instantaneous enthalpy is equal to the internal energy plus any change in work that was done on the system. But we can prove that we can relate work, and I can post this proof if you want. We can relate work so this is mechanical work. Mechanical work can be expressed in pressure times volume. And if you need that proof, by all means, just let me know. All right, so something has, let's say, a piston in a cylinder, classic example. Let's say there's a piston in a cylinder, and I'm going to do some work on this system by moving this piston downwards. And this is, my system is in here, my surroundings are outside, and in the dotted lines are the boundary. So I'm going to change the volume. I'm going to increase pressure, and I'm going to decrease volume. And the multiplication between those two are the amount of internal energy that is going to change, where this used to have internal energy of U, this fluid in here. And now the enthalpy of that system. Enthalpy is it's a measure of it's a measure of disorder and randomness of the fluid itself, and hence related to the energy of the fluid. So now the internal energy also gets more work added to it because of the sum of that pressure times volume. So again, if you want the proof of that, I can by all means draw that out step by step. Okay, this next equation is just rho AV. This equation is actually mass flow rate, so it should really have a dot above it. And remember before we said that mass density is mass per unit volume. So if I'm looking for a mass flow rate, then I would be I would look for a flow rate of that density as well in that volume. That density over that time as well. So what we're going to rearrange here is let's just pretend it's mass right now. I'm going to solve for mass. And so I'm just going to, instead of just saying mass, I'm going to say M. It's now going to be density times volume. Density times volume. Well, I know that volume is the same as area times a distance. So now I have mass equals density times area times distance. Here I have mass equals density times area times volume. And sorry, there shouldn't be a dot there. But if I want it to be a mass flow rate, then it's over time. And I need to take this over time. But I recognize that distance over time is velocity. So therefore, mass over time, which is m dot, is equal to density times area times velocity. And that's where that equation comes from. Now, this should also be m dot. And so this is the density times area times volume. I can substitute in there. and relate that to mechanical work and pressure, if I relate this equation and I relate this equation where I was saying that mechanical work can be expressed as pressure times volume, and I can prove that if you want it proved. And a combination of this equation and this equation will give you this one if that is considered an m dot. Let me change my colors one more time here. And the last equations here are literally just first law energy balances. Now, I would live only with this one. Actually, I would live even with a more simple one. So this is just basic thermodynamics, first law of thermodynamics. Energy can't be created or destroyed. It can only change form. So energy in equals energy out. The potential energy term, let's say something like a turbine, for example. A turbine, sorry, turbine has an inlet, and then it's going to go through a turbine, and then there's going to be an outlet down here. So in is 1, out is 2. Well, there's a difference in height, therefore therefore this elevation difference is going to give us a change in potential energy. There is a difference in velocity going across these turbine blades. Therefore, there's going to be a kinetic energy term. There is going to be work added. Well, it does work on these blades as it's moving. There's going to be, for example, maybe some heat losses. And then there's going to be a change in internal energy because we already had one internal energy in there. So that's what this equation is. It's potential energy term, it's a kinetic energy term, the work energy term, the heat energy term, etc. on one side equals potential kinetic work, heat, etc. on the other side. Then it's just written more specifically because we remember that potential energy is mgh, and we remember that kinetic energy is 1/2 v squared, etc. However you want to write it. So this is just a little bit more specific. I like to just say energy in equals energy out and and just put in all of my energies. This is a very, very specific case of it must be, I don't know, it's probably a turbine or a nozzle or something. I don't know which case this is, but it looks like what's happening is work is being done on the surroundings by the system. And I don't know, there's a change in kinetic energy, there's a change in potential energy, there's a change in enthalpy. I don't know what's going on there, but it's a specific case. And then this is a specific case as well. It's just a case. This is a specific case of the first law energy balance. And this is first law. This is first law. I recommend just knowing how to do a first law energy balance and not memorizing all specific different cases of first law energy balance, because I mean, it's not sustainable in your head. And if we are just memorizing equations without knowing where they come from, then that's just sort of silly. So I hope that that helped the person who was asking this question, and maybe some other people, about some of these common equations in sort of the thermal fluids mechanical energy world.